All right, continuing on, talking about solutions, and let's start with the energetics of solution. So, and this looks a lot like the Born-Haber cycle, uh, if you remember that from last semester. So you start off here, where you have you have a solvent and a solute, and the idea is that these steps here, these are endothermic. They require energy. It's breaking apart the attractions between the solvent and the solute. And then when you mix them together, and this is the case where they mix together and there's more attraction for the solvent and the solute than they have for each other, then this is a overall net exothermic process. And same thing for this case, except it's less than, and then you get an endothermic process. And certain solutions do form that are endothermic. So ammonium chloride, for instance, that one's endothermic, and you can use that in other solutions for like icy cold packs, for instance. So so let's talk about this different cases, and this is also from the last video. If the solute is greater than if the attraction is much greater than its exothermic, for instance, potassium hydroxide, lithium bromide, these are very exothermic when you mix this. Sodium hydroxide as well. If you take solid sodium hydroxide and stick it in water, it gets hot. So it can get really, really hot. You gotta be careful. It actually can boil if you're not careful. And that's important because we use it in industrial processes. And if you add heat to things, then their chemical reactions can increase. So got to be careful with handling this stuff if you have the solid form. If the solute is less than, so this is the endothermic process. Certain things here you can see. So ammonium nitrate, that's a common fertilizer, and silver nitrate, that's another one. These are negative. They're endothermic, and they get cold. And then there's the ones where they're about the same. And sodium chloride is actually kind of even Steven in that regards, but it's a little bit endothermic. But it still goes. So the sodium chloride is very soluble in water. It's amazing. You can get up to about 25% solution. So 3-to-1 water to salt mixture. Pretty high solubility. Okay, so I mentioned sodium chloride. And so look at this equilibrium. We have sodium chloride dissolving into sodium and chloride ions in water. If you have a solution that's saturated, that means that no more sodium chloride will dissolve. And like I said, it's pretty hard to get a saturated sodium chloride solution. You have to dump a lot of salt into something. It's a 25% by mass solution. That's a lot of salt. That's the brine. Unsaturated means more can dissolve. So most solutions, of course, are unsaturated. The ocean water, it's unsaturated. So, but saturated, that's like the Great Salt Lake or the Dead Sea. That's a lot of very, very salty lakes. Supersaturated, that means if you increase the temperature beyond 25 degrees Celsius, then you get more to dissolve. That's called a supersaturated solution, and that's how we make rock candy. So you can make a supersaturated sucrose solution, and then when the sucrose cools, it can crystallize and it makes rock candy. So if you want to how to make rock candy, I used to do that for a lab one time. Okay, and here is the general trend for solubility, and you can see that the vast majority, there's only a few exceptions. Like here you have cerium sulfate. So cerium 3 sulfate is actually decreases in solubility temperature, but everything else increases in temperature. So and quite dramatically, actually, typically speaking, for solubility and temperature. And what about gases, though? So that's solids. So let's talk about gases. Generally speaking, for gases, when you increase the temperature, solubility goes down. Why is that? Well, because of the entropy term. So remember, delta G being negative, delta H minus T delta S. As the temperature goes up, Entropy favors gases being gases, so gases is more disordered than a liquid. So have increasing temperature will lower solubility of gases, and that's important for pollution. There's something called thermal pollution, so you can decrease the solubility of gases, specifically oxygen, in the environment. Also, pressure increases, solubility goes up. That's another one with gases. And we have Henry's law here. Henry's law says the solubility of a gas equals the Henry's law constant times the pressure of the gas. So that's Henry's law. And let's apply it for a problem. What pressure of carbon dioxide is required to keep the carbon dioxide concentration in a bottle of club soda at 0.12 molar at 25 degrees Celsius? So let's look at that. And what is that? The Henry's law constant is 3.4 times 10 to the minus 2 molar per atmosphere for carbon dioxide. I'm looking at my textbook to find the problem. Where are we? Here we go. And so we want pressure. So instead we solve for P. So P is equal to solubility divided by the Henry's law constant, like that. So I'm just taking this equation and solving for P. And so our solubility is 0.12 molar, and the K is 3.4 times 10 to the minus 2 molar per atmosphere. And the molars cancel, and 1 over atmospheres is atmospheres. And the answer is 3.5 atmospheres. So, and you also notice that soda is under pressure. So when you open a can of soda, what do you hear? You hear that pressure coming out, and that's because that's how they do it. They put it under high pressure carbon dioxide to get things to dissolve. So if you want to try this yourself, what is the concentration of ammonia? The brackets means concentration in moles per liter. When the pressure is 0.1 atmosphere, there's the Henry's law constant, and you can see it's 5.8 molar. And if you can see, ammonia has a very high Henry's law constant. Carbon dioxide is fairly high. Both ammonia and carbon dioxide react with water. That's the reason why they're so high. Okay, so let's move on and talk about different things with solutions. These are concentration terms, and you should probably be very familiar with molarity. We used that quite a bit in the previous semester, and it's moles per liter. Next thing I'll talk about is molality, and molality is little m, and that's moles per kilogram solvent. For water, molarity and molality are similar, but they're not the same, so be careful of that. Mole fraction we've also covered. That's the number of moles of something over the total moles. This is going to be important later for calculations. Mole percent is just mole fraction times 100. Parts by mass, the easiest is percent. So you just take the mass of whatever of the total mass times 100. So if you're 20% body fat, that means that the fraction of body fat is 0.2. So if you're 100 kilograms, that means you have 20 kilograms of fat. And then there's parts per billion, parts per million, there's even parts per trillion. You just multiply, for parts per million, you multiply by 10 to the 6. So like 300 parts per million, that means there's 300 parts over a million total. So, and then parts by volume, same idea. We do alcoholic beverages by volume as well. So that's another thing. We do a lot of things by mass, but with the exception of alcohol, we tend to do things by mass instead of volume. So let's go through the example here. A solution is prepared by dissolving 17.2 grams of ethylene glycol in a half a kilogram of water. The volume of the solution is 515 milliliters. What is the concentration of each unit? So let's go ahead and do this. So, and the first one is moles per liter. I've gone ahead, so ethylene glycol is 62 grams per mole, and 17.2 grams is 0.277 moles. So the moles per liter is 0.277. All over liter is 0.515. That's the number of 0.515. That's how many liters are in 515 milliliters. So divide that by 1,000, and then this is equal to 0.538 moles per liter. And then the next one is molality. So this is 0.277 moles per, so half a kilogram of water, 0.5 kilograms. This is going to be 0.554 molal. So a little m is molal. So you can see they're close, but they're not the same. So you cannot substitute molal with molar. And then next thing, percent mass. So it's going to be, this is going to be 17.2, because ethylene glycol is 17.2 grams over the total mass. So half a kilogram is 500 grams plus 17.2 grams. And you put that in your calculator, and then I guess times 100%. This becomes 3.33%. So, and then moles. So it's going to be moles of ethylene glycol. Oh, not the mass. 0.277. That's moles of ethylene glycol, and the total moles is ethylene glycol plus also water. Water, we have 500 grams and then 18 grams per mole for water. So this term here, that's the moles of water. And putting that all together is going to be 9.89 times 10 to the minus third. And is that for mole percent? Mole percent is just the last one times 100. So that's a 3. So the mole percent is 0.989%. So, because it's just this number times 100. Okay. And if you want to try this out on your own, you can try it using this here, a solution prepared by 50.4 grams of sucrose to 0.332 kilograms of water. So you can try that out. And what we'll come up till next time, we'll talk about colligative properties. And why are we doing all this, the different concentration units? Because we need those when we talk about colligative properties. And colligative properties are properties that depend on the number of particles. And the colligative properties I'm going to talk about are vapor, pressure, depression, freezing point, depression, boiling point elevation, and osmotic pressure. And the particles, for instance, if you have ethylene glycol there, that's a molecule, that's one particle. Sodium chloride will break apart into 2 particles. Magnesium chloride breaks apart into 3 particles. So we will pick up there next time.